Hello, good afternoon everyone. Welcome to Liquid Brain. So today I want to talk about linear mixed model, like what is a modeling about, what is linear model, what is linear mixed model, and a little bit of R code in the end to help you to understand the whole process and how you can run the whole analysis in your R environment. So the main content of the video will be like what is a statistical model, what is linear modeling, non-linear modeling, linear modeling with multiple x-axis, multiple input, a little bit on linear mixed model, when to use it, workshop preface, and in the end we're going to go to RStudio and run through the R code on how you can actually run analysis from like previous research which is actually published by the author. Again, you can actually find a link to this slide as well as the R code they're going to use later in your video description down below. So let's go to the first topic, which is what is statistical modeling. So statistical modeling is a process of applying statistical analysis to a data set. So a statistical model is a mathematical representation or mathematical model of observed data. So the best definition I actually heard is about how we can actually generalize the relationship between the two variable so that we no longer need every single measurement at every single point. So for example, if I want to measure a person's weight and their height, if I can draw a line in between the two, I don't need every single weight to every single height, and I can actually understand the relationship between the two data just by that straight line. This allows me to not, I don't need to measure every single height to get a weight, and I can sometimes extrapolate my data to actually predict the other variable. So linear modeling is exactly that. So it's trying to draw a straight line between the two. So for example, if a worksmith can make one toy every 5 minutes, the more time that you give him, the more toys that it's going to make. So you can actually make the time that he uses as an independent variable, so that'll be your x, and the toy that he makes to be y, that's your dependent variable or response variable, so that you can see that it's a linear relationship between each other, and you no longer need to measure every single time how many toys that is make. Okay, so that's the basic of linear modeling. In statistical terms, sometimes we run the y equals to mx plus c slightly differently, where we added something like an error term. So usually we don't specify the error term inside the model when we do like codings and stuff, but just be aware that it is there, and certain literature will call them slightly differently. So just an example of linear modeling where, for example, a person has a glass tank and he put in some marbles. The marble has a specific volume, and the more marbles that he's trying to put in, it will increase the volume of the tank, the volume of thing inside the tank by a certain amount. So you can actually see there's two linear relationship between one another. So I actually pulled this straight from Khan Academy, which is what we talk about the prediction later, where if I want to know exactly 20 liters of water needed, I can actually reverse engineer of how many marbles should I put in. So this is one application of how you can use modeling to solve a certain question. But of course, the world isn't that simple. Linear modeling most of the time doesn't allow you to model or predict or draw a line between the two variables that easily. So one example here will be the dose response curve, where most of the time the percentage growth relative to control and drug concentration is not a linear relationship, but rather a log relationship where you grow very slow and suddenly grow very fast. So I think toxicity has the same problem where it suddenly becomes very toxic to a lot of people. So if you do titration model, that will also be the same type of curve. So in this case, if linear doesn't work, you can also run for something like quadratic. You can run for something like logarithmic and something like exponential. So of course, which model to use on which system require you to really understand the data. The easiest way is just to plot the data out on a curve and see what they do. So that for two-dimensional model, that's pretty straightforward. If it is not, my best advice is find some other paper or some other established scientists or some really good paper and see what model do they use and try to apply the same model so that you get a sense of what it should be before you go in and actually try and error about every single model by yourself. So beside a single model to a single model prediction, most of the time we actually do multivariant modeling, something like that, where you have a linear regression between a multiple x to predict a single y. So you can have, like, for example, if I want to predict the rainfall tomorrow, I can have the wind speed, I can have the altitude, I can have the GPS location, I can have the weather for the 5 days beforehand, the sea levels. I don't know, I'm not very good in weather, but you can have all these predictors to come in and try to predict the rainfall on the next day, on the next year, on the next month, and so on. So yes, instead of actually predicting like a line between the two variable, now you're detecting a hyperplane between the multiple variable and so on. So I think SVM has the same kind of issue, same kind of concept where you're drawing hyperplane in betweens. So like I talked about rainfall just now. So some of the variable that I put in, for example, is it raining the day before or not? It's a yes and no answer. So those are categorical data, where in this case, the categorical data, you cannot run a simple linear regression because it's a yes or no. So we might actually need to run something like a log regression, where you can actually draw a line between yes and no much more easily compared to a linear relationship. So if you have a multivariant modeling, something like that, where one of the input variable or the final output variant is not a linear model, we should call it a general linear model. And you sometimes will hear rich regression, lasso regression, and elastic net regression. Those are the regularization. Yeah, those are part of the general linear model where we try to put penalty in, so we don't really overfit the model, and we try to make the model a little bit more generally representable to our data. I think those deserve another video by themselves. But remember, general linear model, one or few of it where it is not linear. Okay, if everything is linear, it's just a linear model with multiple x. Or I don't know, is that a name for it? I believe there's a name for it. So if you know, just maybe leave in a comment down below. So again, if I did say anything wrong, do leave in a comment. I usually pin it, and just in case, so that I don't continue to mislead people. So this is one of the general linear model example, which we sometimes call it as GLM, where we try to predict the cholesterol level of a person by using the input of their age, their gender, their race, and the frequency of going out to eat. So you can already see that gender and ethnicity are categorical data, and you run a numeric of all this thing into the prediction cholesterol level, you're going to have a really bad time, because male and female, you can put it 0 and 1, not the worst thing in the world. But if you put race as 0, 1, 2, 3, first of all, is how you're going to define 0, 1, 2, 3 between the different race. But if you try to do that, yeah, it's gonna be a problem. So you need something else besides linear regression between the two variables. So then we finally comes into linear mixed model. So this builds on the linear model with multiple input, but some of the input are non-independent from each other. So it's called linear mixed model because we have two types of effects. Okay, we have a fixed effect, which is here, and we have a random effect, which is down there. So if we do something, if you know that something would directly affect the prediction, it's usually called fixed effect. So for example, you put in the time and the toy mix, that's usually what we call a fixed effect. That's pretty straightforward. But a random effect would be something like the variation between individual toy maker and how fast they're able to produce toy. So if you have a single toy maker and you want to know the time and the number of toys they make, that's a very straightforward linear modeling. But now if you have 25 different toy maker and you are trying to understand the relationship between time to make a toy and the number of toy make, it might be very complicated, because some people might need 3 minutes to make a toy, some people 25 minutes. So if you take the average among the two, which is a way to do it, you might not be able to fully capture the picture, because the variation between individual subject is too big. Okay, so in this case, the toy maker individually, we call them a random effect or random factor, and the number of the time to make the toy, it is our fixed factor. So okay, so something like that. So let's go for another example of, let's say, the dose response, the drug of so the effect of the drug to certain individual. So you're giving your drug to all the individual, and you're measuring 5 different dose response. Okay, so most of the time you can see that when you increase the concentration of the drug, it will kill the patient more. But the degree of how it kills differ wildly among different people. Okay, so if you don't consider that, you will have what we call sometimes, I think in this case, called Simpson paradox. I'm not too sure that's exactly the right term. But if you look at the gene expression plot here, you can see the effect between gene expression 1 and gene expression 2. If you look at it on the subject per subject or batch per batch basis, it is a positive correlation. Right? So gene expression 2 is higher, gene expression 1 is higher. But if you look at the general trend without considering the random effect of a different batch, you actually get a completely different prediction, because you just average out between the two. So you can also see that the what is that called? The Pearson correlation, or the power of your statistical significance become way lower if you are trying to actually draw like a line between all of different sample, and worst of all, you might get a completely different conclusion from what the data are actually trying to represent. So linear mixed model is here to try to avoid what we call a sin or pseudo replication. So in this case, we're only actually measuring 10 different data points. Because it's 4 batches, it's actually 10 times 4. So in reality, you only do 10 different replicates. Okay, so the pseudo replication is that we have more replication that we feel like we have more replication than it actually is. So in this case, if you don't consider the batch, it looks like you have 40 different measurements, but in reality, you don't. You only have 10. So it's more of a simulated example. Most of the time, the data trend is not as obvious. So if you do a linear mixed model, then you can actually try to increase your statistical power, and in this case, try to make the result more representable or more easier to generalize among other studies and so on. So yeah, let's go for a workshop in R. So before I go into a workshop, I just want to have a basic idea of what is it about. So in this case, they're trying to predict, rather trying to model the frequency of a person speaking, whether they are speaking higher frequency or lower frequency based on how polite that they are. Okay, so how do they run an experiment? They get multiple subjects, maybe 6 of them in this case, 3 male, 3 female, get them to speak in multiple scenarios. Like most of the psychological data, they don't really have, like they don't tell them what the experiment is actually about. So they just give them a scenario, ask them to speak, and ask them to go home. Okay, so but this data will get their frequency of their speaking, and then they record the frequency of them in each scenario. So like I said just now about the random effect of individual people, everyone speaks in different frequency, even in the same scenario, right? So we have to cross correct for that, and that is where we come in as our fixed effect and random effect, where our fixed effect will be politeness, and in this case gender, but gender is fluid, so I put sex where there's only male and female. So a random effect will be subject and item. So subject is the individual people that we are interviewing, or we are recording, or we are running our experimental on, and item will be the different scenario they're in. So we're trying to, so in this case, politeness here, we're trying to say they are formal or informal, where items here will be like getting a cup of tea, asking for a pay rise, asking to let go of the way. There will be different scenario that they're given themselves. So that will be part of our random effect, because obviously people run it. People even at the same, even in the same polite situation, they might speak slightly differently because of certain words that are pronounced differently, or certain accents that are actually pronounce things in a higher frequency just because they want to. It's hard to say. Okay, so what package we're using in R is called elmer, where we fit linear mixed model into the thing. I find it the easiest to understand, easiest to interpret, and I found a good tutorial about it, which I will show you later. So some things like syntax here, maybe just don't care too much about it. I'll talk to you in the code. And there'll be something called rmel, which restriction maximum likelihood, which I have not fully understand, but I put in some in literature. You can go read yourself on what is it about. So I'm gonna gloss over it, and feel free to leave maybe just email us if you want to know more. I will need to read more of it as well. Okay, so now that comes to our R Studio code. So again, you can download this code on the video description down below. I'll put a link there, and you can actually get what you do. So we can actually run together to see if it runs an error by your side. So every time I have a first chunk as just part of the static, I like to keep it there so that you can, in case I need to change the thing of the output, I'll leave it there. Not very important, you can just glance over. So the first thing, of course, is to load the library in and read the data into an object and remove anything remove any missing data. So after I remove the data, you can actually see this is what it is. We have subject, which is our male 1, female 1, female 3, male 4, male 7, and so on. So there's 6 different people here. Their individual gender, the scenario they're given themselves in, the attitude, which is the politeness and informal, something like that, polite, informal, and their frequency of their speaking. So we're trying to model subject, gender, scenario, frequency to the attitude, something like that. So subject, gender, scenario, attitude onto the frequency to see if we can actually find a relationship between those different things. Okay, so first of all is just to do some basic data exploration where we try to see that formal and male and female and how it looks. So now we already can see in informal they're slightly higher, and in polite environment they are slightly lower. And yeah, between male and female speaks way higher frequency than male, which is also normal. So yeah, so in this case, what we are actually trying to model is this 1, 2, 3, 4. Yeah, okay. So basically, the first thing is attitude and frequency. The attitude will be informal and polite. I don't know what they actually mean, but yeah, kind of an example, kind of a different attitude that they do. And you can see that in informal, they're slightly higher, and polite, they're slightly lower. Yeah, informal and polite makes sense. Okay, so this is the one. But if we just predict these two alone, you realize that the statistical significance is not there. So you just get, there's no statistical significance. But if you look at it, if you separate them out by individual subject, you can actually see a huge increase in the frequency based on the different attitude they're in all of the 6 different subjects they were in. All of the 6 different subject group that we have include our experiment. So we know there's a relationship, right? But you don't see it on an average. So if we look at in different scenario, and you would see that they're not that far different from each other. So that might be not that this. So this is basically our random effect that we're trying to roll out. But in this case, it might not be too significant. And I also plot all the frequency, attitude, individual subject, and individual scenario. So you can actually visualize how individual person. So yeah, this is a plot of every single data point and every single relationship. But you can kind of see that in an informal situation, they have a higher frequency compared to a polite situation based on every single subject and every single situation. So this is what we are trying to model later, just to give a first visualization of it. So the syntax on running elmer is the model that you build is equals to elmer, which is linear mixed model in R, something like that. The target, which is your independent variable, in this case our frequency, we have our fixed effects 1 and 2, and random effect 1 and 2. So in this case, we're going to have attitude over subject scenario. So yeah, we add our other fixed effect in later, don't worry about that. So this just show an example of how you actually put in a fixed effect and a random effect. And why is it 1/random1? I have no idea, but it's just a syntax that I've chosen to use, and maybe it's legacy, I'm not too sure. So how do you actually read the output from a linear mixed model is mainly look at the slope over here. So this is the gradient between the informal, and polite. So in this case, what it is trying to say is, in terms of the frequency, is reduced by 19 Hz when we go for informal to polite. So you can see the attitude here is the column title, and inside attitude column there is two things where you have informal and we have polite. So it will be arranged based on alphabetical order, where you go from I and F to POL. So in this case, from informal to polite, the frequency has dropped by 19 Hz. So we can run again the same thing, including the gender, which again we now get two different gradient, where you can see that from attitude reduced by 19, but gender from female to male, the frequency has been reduced by 108 Hz, which it makes sense because from female to male, the frequency become lower. So this is exactly what we anticipate earlier as well. So the difference between running a model like this and comparing model is that we don't plot a model and we look at the R-square value and say that whether our regression line is a good regression or not. But rather, what we do is that we plot two different models and we take out one component that we're interested in and we compare if the two models is significantly different from each other. So it is why we are constructing another new model called politeness now, which is exactly the same as our politeness model as above from 64 to 69, but without the attitude. So we can see that attitude is removed as one of the fixed effect, and we rerun the model again, we still get the same gender gradient, and then what we do is that, this is exactly the same as the one above, don't worry about it. Then what we do is we run ANOVA between the now model and the actual model that we want to use. So the ANOVA will actually tell us there's a p-value of, for example, in this case, 0.000065534. So we can tell that attitude is a very significant contribution to the overall model, and we can say now confidently that attitude did play an important role in the frequency of a person when they are speaking. Okay, so this is the basic concept of the linear model. But again, we're not done. This video is going to be a really long video because we still have something that we need to talk about. It's called random slope and random intercepts. Okay, so what we talked about just now, as you can see, that we only have a single, in this case, a single slope because we expect everyone to have the same reduction between, for example, male and female, everyone to have about 100. In terms of their politeness, everyone should have a standard drop of -19. To have the same slope but at a different intercept, where we adjust the line up and down instead of the line instead of the gradient of the line. So in this case, most of the time it will work, but in some small situation, it might not do very well. So what we have to do is actually assign a random slope into the calculation as well. You can already see that among different scenario and different subject, all the intercept are different, but all the gradient are exactly the same. So that's what we are trying to change. So how we do that is, there's a syntax called this. So in different subject and different scenario, assign a random gradient towards our subject and scenario in this case. So there's also something called rmel, which is you kind of ignore for now, just leave it as false, and maybe I will eventually make a video about it and I will link more literature you can study in the video description down below. So after you have run this the model, you can actually see that now the intercept and the attitude has completely a different intercept as well as a different gradient. But in general, where we can see that even though they have a different gradient, most of the gradients show a negative 15 to 21 between informal and polite. So our actual, Our actual hypothesis still makes sense. So we're gonna again do the same thing, comparing a model and a now, and we're gonna run our ANOVA again. Again, we can see that now the statistical power is not as high as above, but it's still significant on 0.009. It's still significant between the two models, but not as significant as what we talked about just now. So why do we actually do a random slope intercept? It's actually just to avoid, I believe it's called a false positive, where we actually detect a significance even though it's not there. So this would This will reduce the false positive that you're gonna actually find in your study, and in most situations, having a random slope and random intercept is a better way to run. But of course, that will run into a problem where we don't have enough sample group to actually assign different gradient, because we only have 2 points here. If you have only 2 points, if you only have a limited amount of points, you can't do both. So you need a little bit more data than that. So just for recap, this is linear mixed model. So a modeling is just a way to extrapolate the relationship between multiple variable and try to find a mathematical representation between all the data. And the package we're using is called LME4. And how do you actually run a model is through the elmer function, where we actually try to define the fixed and random effect slightly differently using different syntax, and to compare the difference between the two, we're running ANOVA between the two models. So that will be linear mixed model. Again, this is a very basic introduction to linear mixed model, and there will be a lot more information that I miss out. For anything else, feel free to leave a comment down below, asking a question, or send us an email, and that will help us to learn further on this statistical analysis as well. So thank you for watching, and again, this is gonna be the last time you'll see me in this room, so don't be surprised next time if you see me with a different background. For now, thank you for watching. We'll see you in the next video. Bye.